start the recording. Should we start?
You can
Okay,
start.
recording started, right? Someone started the recording. Okay, so as we know that we had 3.1 linear algebra final exam review. So we had 3.123 and 5.123, 5, and then we had complex numbers and vector analysis. Vector calculus, you can say. We had two parts, vector algebra and vector calculus. But I ask you most of the calcular algebra and quiz too. But you may need, the calculus vector algebra you may need for this topic. So what I am planning is in 3.1, 3.2, two questions here. One question, but maybe 2-3 parts. Okay, and one question from complex number and one question from calculus, right? So this is what I'm planning, 5 problems. So chapter wise, if you look at 3.1 and 3.2, these are basic definitions and how to find determinants, right? In 3.3, we have applications. So mostly you can expect problems from 3.3 because simple determinants are covered in 3.3. So if I ask you to, let's say, find inverse using determinants, then these 3.1, 3.2 are automatically covered, right? So you know that whenever we have a matrix, any n by n matrix, we have to have a square matrix in determinants. So if you have a matrix, then we say determinant of A is basically a number attached to a matrix denoted by DET of A. Sometimes we put bracket as well. Even if you don't put bracket, no problem. A determinant of A or simply determinant of A, or sometimes we write absolute sign, absolute value sign. But this absolute value does not mean absolute value, because if I put a number, X is a number, this means absolute value. But when you have same thing, but inside is a matrix, then it is not absolute value of the.
من الصالون
ابقى ليش 10 الخمسة الأسماء والخمسة بلدان.
زي هين الخمسة ما الصالون، هين الخمسة بخمسة تو.
المايك مفتوح ترى.
أيوة.
Can you
ثلاثة
stop the mic, Seal? Someone's mic is open. Now it's off. Okay. So, all right. So when we write absolute value of a determinant of a matrix, it means determinant, not the absolute value. Okay. Anyway, these are the 3 notations for that, and it is a number. It is a number associated with a matrix, right? It is a number. We all know that associated with matrix A. We had many methodologies. If we have A, B, C, D, a 2x2 matrix, and we want to find determinant of this, it can also be written as straight lines, and you write only the entries of the matrix. A, B, C, D, if you draw straight lines, it means it's not a matrix, it's determinant of a matrix. So it is AD minus BC. You multiply the diagonal elements and minus the off diagonal element, right? So this is a determinant of a 2x2 matrix. but if you have higher than that, let's say A, B, C, D, E, F, if you have a 3 by 3 or more, GHI, let's say this is a matrix and you want to find the determinant, right? Then it is not that simple. Then what we do, we choose any row or any column. Let's say if I choose column row 1, right? Then I will pick this number first, A. I will remove the row and column of that number A, and I will multiply A with a determinant which is obtained by deleting the row and column of the number A. So the leftover is EFHI. EFHI, this one, right? Then I will go to the second one, B. And it is with minus B. And now I will remove the row and column of this B. So I got DFGI. DFGI. And then I will go to the third one, which is C. C will again come with plus. And now I will remove the row of C and the column of C. So you got DEGH. DEGH, right? So this is your determinant. That's it. We only choose one row. So this is called expansion. This is called cofactor expansion. Expansion across row 1. So we choose the row 1 and we expand the determinant. And now we know that how to find 2 by 2 determinants, right? These 2 by 2, we know that we multiply E with I minus F, D with I minus GF, H D minus GE. So we know that. So we can complete this, get the answer. You can choose any row, any column, the answer will remain the same. You can choose third row or third column, second row, whatever you want. So we can expand across any row or any column. This is our choice. Your answer will be same. Okay, this is our choice. So this is one good thing basically, right? Anyway, there is another way of finding a 3 by 3 matrix, A, B, C, D, E, F, G, H, I. For 3 by 3, there is another way of finding the determinant. They say, OK, you repeat first 2 rows, write them outside. A, D, first column and second column. Repeat first and second column, write them outside. And now multiply first diagonal with plus, second diagonal, again multiply with plus, write third diagonal with plus. OK, and then of this diagonal, opposite diagonal, write it with minus sign. See, these are diagonals with minus sign. This is a third diagonal with minus sign. Add these 3 diagonals. OK, add this diagonal, whatever the answer is, right? And subtract the top 3 diagonals, whatever their answer is. We multiply them. OK, so this will also give you the determinant of a matrix. It's a shortcut. It is given in your exercise. I can show you. If you go to the exercise. If you go to this exercise 3.1, you can see this thing is given in exercise here. See exercise 15-16. You can write 3 by 3, write first column, second column again, multiply these 3 diagonals. There are only 3 complete diagonals. This is not a complete diagonal. You see only 2 entries, 3 entries, 3 entries, 3 entries. That's it. And then here 3 entries. You can easily write the determinant by this method as well. Anyway, so we know how to do this. So these are given in 3.1, 3. In 3.2, there are some properties as well that if you have a diagonal or triangular matrix, D, E, G, H, I, you see it's a lower triangular. We have diagonal elements and above the diagonal, everything is 0. So the determinant of this triangular matrix is just A into E into I, means you can just multiply diagonal entries. That's it. Product of diagonal entries. This is again a shortcut. Or if it is A, B, C, E, F, G, H, I. Now you see it's upper triangular. Now below everything is 0. Still the answer will be A, E, I. So upper triangular and lower triangular matrices both give you the same answer, product of the diagonal entries. So these are some shortcuts as well. Also in 3.2, they said you can use the row and column operations as well. Can also use row or column operations to reduce the matrix into lower or upper triangular form.
Mister, in the exam, will you ask a specific way of solving, or you'll just say find the determinant? We can use any of the.
Find the determinant. Yes, find the term. It's your choice how you find it.
Yes, okay.
So I'm just summarizing all the methods. Okay. So we can use row column operations that we use in chapter 1, right? So for example, if it is, let's say, in the exercises, if you say it is 104232 and 05 minus 2. It is not triangular because this 2 is not 0, this 5 is not 0. If you want, you can reduce it first. Reduce it to, you can use this 1 to make this 2 0, R2 minus 2 R1. Nothing will change. Determinant will remain the determinant. Let me use this one. Instead of writing DET again and again, I can use straight lines. So 2 minus 2, 0, 3 minus 0, 3, 2 minus 8 is minus 6. And then 0, 5 minus 2. Now I can make this 1, right? So, but if I make this 1, I have to divide R2 by 3. 1, 0, 4, 0, 1 minus 2, 0, 5 minus 2. But in determinant, when you divide some row or column by 3, the whole determinant gets multiplied by 3 to adjust it. OK, so basically, if we basically took 3 as common from row 2. So 3 comes outside, it becomes 0, 1 minus 2. OK, in matrices, we don't write 3 outside, but in determinant, you have to adjust. Now use this one to make this 5, 0. So R3 minus 5R2. And determinant does not change with row replacement operation. No need to adjust anything if you are replacing a row by a multiple of another. So it will become 0, 5 minus 5, 0, and minus 2 plus 10, 8. Now you see it is lower triangular. Everything is 0 below the diagonal. Now I can write the answer as this determinant is 1 into 1 into 8. 1 into 1 into 8. Why? 1 is here, 1 is here, 8 is here. So the product of diagonal entries. So the answer is 24. So we can reduce a matrix to lower triangular or upper triangular form and then use the property that its determinant is the product of the diagonal entries. So you can do this as well. So it's your choice. You want to go this cofactor. This is called cofactor expansion. OK, so cofactor expansion, you can do that across any row or any column. That's your choice. Any row, any column. Or you, for a 3 by 3 matrix, you can use this idea as well, which is given in the exercises. Or you can use this property by reducing the matrix into lower triangular form or upper triangular form. Echelon form, you can say that. If one row is 0, then determinant is 0. If you are finding a determinant of a matrix whose row is 0, one row or one column, if one row or one column entirely is 0, then the determinant is 0. No need to do anything. If 2 rows or columns are identical, same, right? then determinant is 0. If you see two rows are same or identical, 0. If you see one row or one column, if a row or column is multiple of any other row or column, multiple of any other row or column. So basically row has to be a multiple of row and column has to be a multiple of column. Then determinant is again 0. So these properties can also help us. For example, I think there are some matrices where they use properties of the determinants. Here it is using cofactor expansion. Somewhere there will be properties, and maybe in section 1, no, section 2, because properties are in section 2. So here you see they said illustrate the property of a determinant. Don't solve. So here what you did, I think we interchanged row and column. Row 1 becomes row 2 and row 2 becomes row 1. If you do that, if you interchange any two rows, two columns, there is a minus sign. You have to remember that as well. Here we used 1 to make this 0. Multiplied this by -3 and add in row 3 and nothing changes. The row replacement operation does not change the determinant. OK. Similarly, if any two rows columns are identical, their determinant will be 0 as well. Anyway, important things are in 3.3. There are two things which are important and they use determinants. That's why most importantly, I will ask you questions from here. There is two things. One is finding inverse using determinant, finding A inverse using determinants, basically using cofactors. This is what should I say? But cofactors are basically coming from determinant. So basically using the formula, this A inverse is equal to 1 over determinant of A into adjoint of A, right? So this is a formula of using inverses, and you can expect a question like this, where I will give you a matrix and I will ask you to use this determinant, this formula to find the. So for example, if I go to exercises, let's say I can pick 14. 113 minus 221. A inverse exists if and only if determinant of A is not equal to 0. If determinant of A is 0, then inverse does not exist. OK, so we need this one. So we should start by finding the determinant. 0, 1, 1. If the determinant of any matrix is 0, if A is this, question is find A inverse using this formula, using adjoint or adjugate. This is adjoint of A, or another name is adjugate of A. Adjugate of A. So basically we need to use this formula. So let's see. First of all, find the determinant. Determinant is, if I can use first column, you see. I can use first column. Why I'm using first column? Because there is 1 0. 0 helps us, right? So I'm using first column. It means I'm using 1 and then remove this row and this column. So you got 2 1 1 1, 2 1 1 1, and then go to here -2, right? But second uses minus of -2. Now this row is gone. So you got 1 3 1 1, 1 3 1 1. Now this is not there, right? So this 1 and 3 are there. So that's why we got 1, 3, 1, 1. Now the third one will use this one. Third one is this. So this row and this column is gone. So 1, 3, 2, 1. So plus, because the third one is 0, so I can just leave it 0. No need to write anything with it because 0 will make everything 0. So now it will become 1 into 2 minus 1 plus 2 into 1 minus 3. So that becomes 1 and minus 4. That is minus 3. So not equal to 0. So it means we are OK. So what is adjoint? Adjoint is the cofactor matrix, transpose of the cofactor matrix. For adjoint, we use C11. OK, Cij is called cofactor of Aij. Cofactor of Aij. This is equal to minus 1 to the power I plus j, means sign. If I plus j is even, the sign is plus. If I plus j is odd, sign is minus. And then we write a determinant of the matrix whose ith row and jth column is removed. Aij by removing ith row and jth column. Ith row, jth column. So basically, I will find this Cij for all the entries. For example, C11. 1 plus 1 is even, so minus 1 to the power 1 plus 1 will become 2, and it is positive. So no need to write. We know it's plus. Now this is the first one. You see here, I can 1 minus 2, 0. So I can remove it. 1 minus 2, 0, 1, 1, right? So C11 is for A11. This is A11. Remove the row and column. This is the matrix Aij. This is the Aij matrix. So 2, 1, 1, 1. So which is essentially this one. So this was basically the cofactor C11, which we did. This is the cofactor of C21 because this is for second, right? So anyway, what is the answer to this one? It is 2 minus 1 is 1. So C11 is 1. Then I will go to C12. C12 is negative. Why negative? Because minus 1 to the power 1 plus 2. 1 plus 2 is 3. Now C12 is this one. This is A12. I will remove this row and this column. So I got minus 2, 1, 0, 1. I got minus 2, 1, minus 2, 1, 0, 1. Right? So minus 2, 1, 0, 1. So that is equal to minus 2 minus 0 and minus from outside. So your answer is plus 2. Then the third one is C13. C13 is minus 1 to the power 1 plus 3, which is again positive. So see, whenever your sum is odd, I plus j is odd, you will write a minus sign, right? So see, 1 plus 2 is odd. Odd gives you minus sign. 1 plus 1 is even. Even gives you plus sign. That's how you remember. This is odd. Again, it will give you minus sign, right? But C13 means this is first row, third column. C13, first row, third column is gone now, right? This is gone. So you got minus 2, 2, 0, 1. This one, minus 2, 2, 0, 1. That's how you complete it. So now the answer is minus, this is plus now because minus it's even. 1 plus 3 is even. So even gives you plus. So minus 2 minus 0. So it is minus 2. So these are three cofactors. Now I will continue. I will write C21. C21 is minus. Minus of 2, 1 is this, right? So this row, this column is gone. So 1, 3, 1, 1. 1, 3, 1, 1. So you can use the pencil and keep erasing. After each cofactor, erase those lines so that you don't have to make mistake. 1 minus 3 is minus 2. So minus minus 2 is plus 2. Then C22. C22 is again plus. Now second row, second column is gone. second row, second column is gone. So 1301. 1301. So you got 1 minus 0. So the answer is 1. Then C23. C23 is again minus because 2 plus 3 is odd. So odd gives you minus, right? So you can directly write this. And 2, 3 means second row, third column, this one. So this row, this column is gone. So 1, 1, 0, 1, right?
1 1
1,
0
1,
1,
0.
yes.
1 1 0 1. So what you can do is whenever you find cofactors, use pencil here, pencil and erase pencil right away, and then make a circle. So let me clean it again. 1 minus 2 0. Let me clean it again. 1 minus 2 0 1 1 0. No, it was not 0. Let me check. 1 3 2 1. 1 3 2 1. Right. So every time when you erase it, now we are here. C31 is this third row, first column. Make these two lines 1 3 2 1. Write it here and then erase after that. Right. 1 3 2 1. So C31 is plus. C31 is plus and 1 3 2 1. This was it. 1 3 2 1. Yes. 1 3 2 1 is 1 minus 6 minus 5. Then C32. C32 is minus.
Sir, you did not write the answer for C23.
What is that? Minus 1, right?
Yes.
1 minus 0. So 1 and minus from outside. So minus 1. And now this is the next one. This one. So again, if you erase this, you have a clean matrix again. Because if you use pencil, write the numbers with the pen and then use pencil for the lines. Then you can erase the pencil and your matrix will not be erased. So if you remove these two now, so 1 3 minus 2 1. 1 3 minus 2 1. So this will become 1 plus 6, right? 1 plus 6 is 7. So minus 7. And then the last one is C33. C33 is again plus. Right. So it is again plus. Now if I write 3 means the last one, which is this one. This one, right? See, 3 is gone. So you got 1 1 minus 2 2. 1 1 minus 2 2. So this is 2 plus 2 4. So these now I will write adjoint. Actually, C is called a cofactor matrix, which is C11, C12, C13, C21, C22, C23, C31, C32, C33. This is a cofactor matrix. This is called matrix of cofactors or cofactor matrix, right? But then adjoint of A is the transpose of cofactor matrix. It is C11, C12, C13 means write the first row as first column. 2 1 2 2 2 3 3 1 3 2 3 3. So if you want, you can skip this. You can directly write after that. You can directly write adjoint, but write first row as first column. So this was first row. You see, this was first row. 1 2 minus 2. 1 2 minus 2. So I can write this as first column. Then 2 1 minus 1 was second row, but I'm writing it as second column. And then minus 5 minus 7 minus 4. So minus 5 minus 7 and 4. So that is your inverse. Okay. So that is your inverse. Not this is adjoint. Therefore, A inverse is 1 over A into adjoint of A. You have to divide by the determinant. Determinant was minus 3, right? 1 2 minus 5 2 1 minus 7 minus 2 minus 1 4. And now you can divide all the numbers by 3. So it will become minus 1 by 3, minus 2 by 3, 5 by 3, minus 2 by 3, minus 1 by 3, 7 by 3, 2 by 3, 1 by 3, and minus 4 by 3. So this is the inverse of the matrix. Now you can also check. You can check whether your inverse is correct or not, right? You can verify whether it is correct or not. How? We can multiply A with A inverse and your answer will be I. Write A here. 1 minus 2, 0. 1, 2, 1, 3, 1, 1. Right? And you can multiply this one. Instead of multiplying this, we can write this one. 1, 2 minus 5, 2, 1 minus 7, because it will be easy to multiply this matrix, but minus 1 by 3 is outside. This is outside, remember that. Okay. So if you multiply, your answer will become minus 300. If you check it, it will be minus 3000 minus 3000 minus 3. And then when you multiply by minus 3, it will become identity. So how we multiply matrices? First row with first column. 1 into 1 plus 2 minus 6. 1 plus 2, 3 minus 6 is minus 3. You see? And then first row with second column. 2 plus 1 minus 3, 0. Minus 5 minus 7 minus 12 plus 12, 0. Second row, first column, minus 2 plus 4 minus 2, so 0. Minus 4 plus 2 minus 1, again minus 3. 10 minus 14. 10 minus 14 is minus 4 plus 4 is 0. 0, 2 minus 2, 0. Second row, second column, 0, 1 minus 1, 0. Third column, 0, minus 7 plus 4 minus 3. See? So it's not that I wrote it. If the inverse is correct, then I will get this. Now if I divide, it will become 1 0 0 0 1 0 0 0 1, and this is identity. It means my answer is correct. So it's always a good idea to multiply A with A inverse and check if you get identity or not. If you get identity, it means your answer is correct. So this is how you find them.
Can you repeat the check?
A check. Check is just the multiplication, right? What I did, I wrote a matrix A here, and I wrote the matrix A inverse. A inverse was by 3 by 3 by 3, right? But multiplying 1 by 3 and adding it will be difficult. So what I did, instead of writing this inverse, I wrote this inverse. This is also the inverse, right? 1 over 3 into this matrix. So I wrote this 1 over 3 at the beginning. And I wrote only adjoint here. This is not inverse. This is basically adjoint, right? But I wrote this. This with adjoint is basically A inverse. So it was easy to multiply these two matrices. That's why I wrote 1 over determinant of A separately. Now we multiply first row with first column, right? So 1 into 1 plus 1 into 2 plus 3 into minus 2. So 1 into 1 plus 1 into 2 is 3, plus 3 into minus 2 is 6. So 3 minus 6 is minus 3. Okay, so this was 1 plus 2 minus 6. And then first row with the second column. So it will become 1 into 2 plus 1 into 1. So 2 plus 1, and then 3 into minus 1. So see, 2 plus 1, 3 minus 3 is 0. Then the first row with the third column. This was in chapter 2, right? In midterm, 1 into minus 5, then 1 into minus 7, and then 3 into 4, 12. So see, minus 12 plus 12, 0. 3 minus 3, 0. And 3 minus 6 minus 3. Similarly, you will go to second row, first column, second row, second column, second row, third column. You will get these three numbers. Then you will go to third row, first column, third row, second column, third row, third column. You will get these three numbers. All right. So this is the multiplication that will exactly give you the identity matrix. And this is the check, because this is the definition of inverse. When you multiply A with A inverse, it gives you identity. If it does not give you identity, they are not inverses of each other. So if they do not give you identity, then go back. Maybe some cofactor is wrong. We may have calculated some cofactor wrongly if it does not give me the identity. The second thing in 3.3 was a Cramer's rule, which was, so again, important static, right? Cramer's rule, if you have a system of linear equation ax equal to b, and you have to solve this using Cramer's rule, what we do, first we find the determinant of a. If it is not equal to 0, go ahead. We can use Cramer's rule. Okay, we can use Cramer. If determinant is 0, we cannot use Cramer's rule. So of course, determinant will not be equal to 0. Then we define matrices A1, B. Let's say my determinant is, my A matrix is first column 1 is A1, column 2 is A2, column n is AN. Let's say so the determinant of this was not equal to 0. When I took the determinant, calculated, it gave me some number which is non-zero. So then I will write A1B. A1B means in the first column, replace first column by B. What you should do, replace first column by B and write all other columns as it is, A2, A3, AN as it is. And find the determinant of this as well. Determinant of A1B. This can be 0, no problem. Any determinant, 0 or non-zero, no problem. Then go to A2B. In A2B, write the second column. Replace the second column by B. You don't have to use these colors. I'm just using these colors to explain that second column is going to be, okay? And then all other columns remains as it is. So second column will become B. And similarly, the third column, fourth column. If it is a 3 by 3 matrix, then of course there are only 3 columns, right? If it is 4 by 4, then there will be 4 columns and we keep on going. So let's say if it is just 3 by 3, let's say I can make it simple. If it is 3 by 3 matrix, right? Then you will find the third column as it is, third column as it is, right? And again, you can find the determinant of this A to B as well, and you get any determinant. Then you go to the third column. So the third column is replaced by B. You see, the third column is replaced by B. So you got another matrix, you can get the determinant of that as well. So you have now these 4 determinants. So Cramer's rule says that because if you have a 3 by 3 matrix, it means there are 3 unknowns, x1, x2, x3. So the determinant of A1 divided by determinant of A gives you x1. Find that. Determinant of A2 divided by A gives you x2, and determinant of A3B divided by A gives you A3. So that is a method that can solve any system where A is a n by n square matrix whose determinant is non-zero. So for example, where is 3? These are the Cramer's rule here. You see, 2 by 2, 3 by 3. So these two here, I will only have A1, A2, right? Only A1, A2. First of all, you have to write the matrices. For example, question number 4, -5 to 9. Right? -5 to 9. And 3 minus 1 minus 4. This is a system of equation, right? I will write this system as AX equal to B, right? So what is AX equal to B? Where A is the coefficient matrix, -5, 2, -3, 1. -5, 2, 3, -1. Coefficient matrix, just the coefficients. Then B is the right hand side, 9 and -4. And X is your unknown vector, x1, x2, right? We don't need that. I only need a and b. So first of all, I will find the determinant of a, which is minus 5, 2, 3, minus 1. So that is 5 minus 6, which is minus 1, not equal to 0. Go ahead, right? This is good. Now I will define a1b. A1b means replace the first column by b. B is 9 minus 4, second column as it is. And define A2b. A2b is first column as it is, minus 5, 3, second column replaced by b. So see, here b is in the first column, here b is in the second column. There is no A3. Why? Because there is no third column in A. If you have a 3 by 3 matrix, then there will be A3 as well, because there will be third column. So now I will find the determinants of these two. Determinant of this will be 9 minus 8, minus 9 plus 8, which is minus 1. And determinant of A to B is 5 4s are 20, minus 9 3s are 9 3s are 27. So that is minus 7. So hence, therefore, Cramer's rule says that your solution of the system is x1 is a1b divided by a, which is a1 is minus 1 and a is also minus 1. See, this is a, right? So that answer is 1. And then x2 is a2b divided by a, which is minus 7 by minus 1. So that is plus 7. So this is your solution. That's your answer. If you want to check your answer, what you can do? Optional, check is optional. X1 is 1, x2 is 7. Replace it in the equation. And the first equation is minus 5x1 plus 2x2. So equation 1, minus 5x1 plus 2x2. So that is minus 5x1 plus 2x2. So that is minus 5 plus 14, which is 9. See the right hand side, right? What is the second one? See, this is the 9. 3x1 minus x2 should be equal to minus 4. 3x1 minus x2. Second is 3x1 minus x2. So 3x1 is 1 and minus x2 is 7. So 3 minus 7 is minus 4. That is also correct. See, both are same, 9 and minus 4. Hence, my solution is correct. No mistake has been done. So check is optional, but it's very good idea. And you don't have to even write this check. You can do it in your mind. Let's say, just do it in your mind. OK, minus 5 into 1 is minus 5 plus 2 into 7 is 14. Minus 5 plus 14 is 9. So that's OK, right? So you can just do it in your mind so that you have your answer is correct. Okay.
Mr. And it's the same thing for 3 by 3 and a 4 by 4. You just
for 3 by 3, you will have 3, exactly the same thing. You will have another one, right? If it is A3. 3 by 3, then you will have another A3b, yes, right? Okay. So there will be an extra A3b where the first column will be as it is, second as it is, third column will be B1, B2, B3, right? And then you will find the determinant of that as well for 3 by 3 case, right? So there will be third one as well. So and then you will find the determinant of that. And because for 3 by 3 matrix, you will have x3 as well, right? So x3 will be a3b divided by a. So that will give you a third answer. So if you see the I think if you go to the Cramer's rule section, I think I have done 3 by 3 as well. There will be some solution maybe here. Class notes 3 by 3. So see here, this is about the determinants. This is the Cramer's rule. I did this 2 by 2, and I think there will be a 3 by 3 as well here. Right? So exercise 5 was 3 by 3, which is done here. So I wrote A and B. I found the determinant of A, which is minus 8 not equal to 0. So we write A1B, A2B, A3B. We write them So see 302. This is B, right? 302. So see 302 in the first column, 302 in the second column, 302 in the third column. Then we found the determinants of all these three matrices and divided all these three determinants by the determinant of A, which is -8, -8, -8. So it gives you x1, x2, x3. Okay, so you can see that solution as well. You can solve exercise 5 and compare with this one and see if you get the answer. So of course, chapter 4 is not there. Chapter 5 is there. In chapter 5, you have eigenvalues and eigenvectors. Basically, 5.1, 5.2 are same. You can jointly do that. If you attempt any problem from 5.3, 5.1 and 2 will automatically be covered. Anyway, in chapter 5, basically 5.1 plus 5.2 gives you eigenvalues and eigenvectors. In what are eigenvalues, eigenvectors? If a matrix A is given, we are looking for a vector X that gives you some number times the same vector back. If any vector satisfies this property, then X is an eigenvector. If X is an eigenvector, if AX equal to lambda X for some value lambda, some real number lambda. Lambda can be anything, 1, 2, 3, 4, whatever, -2, -1, -1/2, whatever. If they give you a vector, given a vector, let's say V, and a matrix A, right? To verify if these are given, and you have to verify only to verify that whether or to verify that V, a given vector V, is an eigenvector of A, right? What you have to do, what we will multiply. If they are asking you this one to verify, we will just multiply A with V. We will write a matrix A. We will write a vector V. We will multiply, get a vector. Whatever vector you get, you will try to write a number here so that this inside function becomes V. Means you get some number lambda and your V comes back. Try to write like this. Okay, if you are able to write like this, it means it is an eigenvector. Otherwise, it is not an eigenvector. So verification is easy. Verification is easy if a vector is given. Here you see here like this one. Is this vector an eigenvector of this? So what you will do in exercise 3 in 5.1. Let's say a matrix was given. So I will just multiply vector with a matrix. Matrix was -3, 1, -3, 8. Vector was 1, 4. So you can multiply. First row, first column. So -3 into 1 is -3 plus 1 into 4. So -3 plus 4. Then second row, first column. -3 plus 32. So this will become 1 and 29. Now you see, no matter what you do, you will never be able to write this as a constant into your V back. What is your V? V is 1, 4. V is 1, 4. Can you write this as 1, 4? No way. You can try any lambda here. 129 will never become 1, 4. So it means this is not an eigenvector. It means 1, 4 is not an eigenvector for A. Eigenvector of A. V is not an eigenvector. If V becomes an eigenvector, then this lambda is called the eigenvalue. If you get this eigenvector, If this is true, then this lambda is called eigenvalue for that eigenvector. So that's why in the question they ask you, if so, if it is an eigenvector, then what is the eigenvalue? If it is an eigenvector, then eigenvalue automatically comes. See, if your matrix becomes lambda here, then I will say that this is my eigenvalue, no issues. But if V does not become an eigenvector, I don't have to give you any eigenvalue. There is no eigenvalue. Okay, so maybe another problem you try, it may become the second one, or maybe this one. You can try this, multiply this matrix with the vector, see if your vectors come back with a lambda. The same vector should come back here with a vector lambda, then this lambda will be the eigenvalue. So verification is not difficult. The problem occurs when a vector is not given and we have to find the vectors. To find the vector, an eigenvalue must be given. You see here, they also ask me that these are the eigenvalues they are given. Find the eigenvector. So if lambda is equal to 5 is my eigenvalue, what is the eigenvector that gives you 5x? Because lambda is given. So I put lambda here. So here I will find the vector x. OK, that x will be the. So it means I have to solve this system. I have to solve this system going back to chapter 1. So if eigenvalue is given, I can find eigenvector. If eigenvector is given, I can find eigenvalue. The problem is when both are not given, what should I do? Right? From scratch. So that is in 5.2. Finding the eigenvalues and eigenvector. Five, 3, 3, 5. Let's say. So important is this. Finding eigenvalues and eigen. So first thing is, if a matrix A is given, we solve a determinant of A minus lambda I and put it equal to 0. OK. Or you can write determinant of A minus lambda I and put it equal to 0. What is A minus lambda I? We just subtract lambda from the diagonal of A. Subtract lambda from diagonal of A. That's how you get it. And once you get the eigenvalue, then we solve A minus lambda I x. Now this is a matrix, not determinant. A minus lambda I, because lambda is known here, equal to 0 for x. We solve this for x to get the eigenvector. We solve this for lambda to get the eigenvalues. OK, so let's do an example. A is, let's say, what is that? 277253353 3 minus 2 1 minus 1 1. That's it. So to find eigenvalues, I have to solve for eigenvalues determinant of A minus lambda I equal to 0, right? We have to solve this for lambda, right? The eigenvalues. First, we will find eigenvalues. So what is A minus lambda I? Subtract lambda from the diagonal. 3 minus lambda, minus 2, 1 as it is, and minus 1 minus lambda. Okay, put it equal to 0. You don't have to use the color. I'm just using it so that you remember that we are subtracting lambda only from the diagonal. Okay. Now here multiply this 3 minus lambda into minus 1 minus lambda minus 1 into minus 2 equal to 0, right? This minus this. So see, this is an equation in lambda. No x, nothing is there. So 3 into minus 1 is minus 3. 3 into minus lambda is minus 3 lambda. Then lambda into minus 1 is plus lambda, and lambda into minus lambda is plus lambda square. And here it is minus minus 2, which is plus 2 equal to 0. So I can write lambda square first. Then minus 3 plus 2 is minus 2 lambda, and minus 3 plus 2 is minus 1 equal to 0. Right? So are there any? So I think this was not a good choice. Not a good example. The reason is I think my answers are not whole numbers. I have to use, because there are no whole numbers as the answer. I have to use the quadratic formula. 2 plus minus 4 minus plus 4. See, so we got something in the 4 2s are 8. So 2 square root of 2 divided by 2. So it is 1 plus minus square root of 2. So these are two eigenvalues, right? 1 plus and 1 minus. So one eigenvalue is lambda 1, which is 1 plus square root of 2. One eigenvalue is lambda 2, which is 1 minus square root of 2. So these are two eigenvalues. For eigenvectors, this will become little difficult. So it's not a good example, but they only ask me the eigenvalues, right? Characteristic polynomial and eigenvalues. This is the characteristic polynomial. This is called characteristic polynomial. Okay. This is characteristic polynomial. So basically, the polynomial that we get from here, right? This one, this is called characteristic polynomial. So he said find the characteristic polynomial, and after that find eigenvalues. So after that, if I solve this, we get eigenvalues. So this is basically characteristic polynomial. To find eigenvalues, I think we should do some other eigenvectors. Okay, for eigenvectors, we should do some other example. Maybe I can do that example where eigenvalues were given to me. Right, I can save time now. Let's say I have for lambda 4, I have to find the eigenvector. 5 0 2 1 1 5. So if I solve A minus lambda I, determinant of A minus lambda I equal to 0. If you solve it, you will see that you will get lambda 1 and lambda 5. These are the two values that you will get. Lambda 1, lambda 5, 5 0 2. You can verify that. OK, do it as an exercise. Do this. After finding the eigenvalues, I can find eigenvector for one by one. First of all, I will consider lambda equal to 1. Lambda equal to 1, so I have to solve A minus lambda 1 I. So lambda is 1, so it becomes A minus I x equal to 0. I have to solve this. To solve this, I will only write this matrix. I will not write the system. I will write this matrix. This matrix is subtracting 1 from the diagonal. 5 minus 1, 0, 2, 1 minus 1. So 4, 0, 2, 0. Sorry?
Can you repeat?
This thing?
Yes, from when you said we'll choose lambda is equal to 1.
Yeah, so we have to solve for lambda 1. We have to solve this now. A minus lambda I x equal to 0. A minus lambda I is a matrix, but lambda is 1. So this lambda is 1, right? So it means it is A minus 1 I. 1 I means I, no need to write 1. But if you write 1, doesn't matter, you can write 1. So see, I'm subtracting 1 from the diagonal, right? A minus 1I means subtract 1 from the diagonal. That's it. Subtract 1 from diagonal. That's what I did. And now I'm not finding determinant or anything. I'm writing the augmented matrix and solving the system, right? So if I use this 4 to make it 0, I can write R2 minus half R1. So R2 minus half R1 will make it 0, 0. One of the row will definitely become 0. Always remember. And from here, if I write the system, it is 4x1 plus 0x2 equal to 0. And from the second, it is 0 equal to 0. Right? So it means I got x1 equal to 0. From the first one, x1 equal to 0. And x2 I did not get, so it is free. One of the variables has to be free in eigenvector. So therefore, I will write my eigenvector x is equal to x1, which is 0, x2 is free. So I can write x2 as x2. So x2 and 0, 1. So this is my eigenvector. My eigenvector v1 is just 0, 1. Just pick this thing. Just pick this and call it the eigenvector. That's it. Leave x2. x2 is free. I can call it 1. x2 equal to 1, right? So basically, I can call x2 equal to 1. So I got this eigenvector 0, 1. Now for the second eigenvalue is 5, right? So I can solve a minus 5I x equal to 0, right? So lambda is 5, so I have to subtract 5. So I will write now a minus 5I. What is this matrix? A minus 5I. A minus 5I means subtract 5 from the diagonal, right? 5, 0, 2, 1, 5, 0, 2, 1. And I'm subtracting 5 from the diagonal. So you will get 0, 0, 2, minus 4. So one row is already 0, no need to reduce it. So I can just directly write first row gives me 0 equal to 0. Second row gives me 2x1 minus 4x2 equal to 0. So this implies that x1 is equal to 2x2 and x2 is. OK, you can write like that. X1 is 2x2. So now your x becomes x1, x2. X1 is this, x2 is x2. Basically, your vector is x1, x2. So your x1 is 2x2, right? And x2 is free, so it is x2. Take x2 as common, you got 2, 1. So the second eigenvector is just 2, 1. Just pick this one, right? So this is your second eigenvector. So that's how you can find eigenvalues and eigenvectors. After finding eigenvalues, eigenvectors, in 5.3, they have a topic which is diagonalization. Diagonalization means finding a diagonal matrix, D and invertible matrix P. And you see the answer will be in just one line. P such that A is equal to P D P inverse. This is what diagonalization means. Diagonalize A means find this one. So basically, solution is very simple. If A is given, matrix is given, right? We find eigenvalues. We find eigenvalues lambda 1, lambda 2, etc. OK, we find eigenvectors v1, v2, etc. Right? Eigenvalues, eigenvectors, so on. And then we just write matrix D. Then your diagonal matrix D is writing lambda 1, lambda 2 on the diagonal. Everything else is 0. right? Whatever, if it is 2 by 2, we'll stop here. 3 by 3, we'll stop here. 4 by 4, we'll stop here, right? And so on the diagonal, we have eigenvalues on the diagonal and off diagonal elements 0. That's why it's a diagonal matrix. Everything above below is 0. And your matrix P is your first column is first eigenvector, second column is second eigenvector, third column is third eigenvector, and so on. That's how you write. So let's say in the above example, if someone asked me to diagonalize this matrix 5, 0, 2, 1, right? Diagonalize matrix A, which is 5, 0, 2, 1. Let's say this is the question. So what I will do, step 1 is I will find eigenvalues. We have already found that, right? Lambda. So lambda 1 was 1, lambda 2 was 5, right? Step 2 is find eigenvectors. We have found for this matrix, I got V1, 0, 1 and V2 was 2, 1, right? Yes, V2 was 2, 1. We got that. Now I will write D. So if I ask you this, I can split that. Let's say I give you a question that a matrix A is given, find the eigenvalues and eigenvectors of these matrices. So you have already found eigenvalues, eigenvector. After that, I can ask you, OK, now write the matrix D and P. Now write down the matrices D and P such that write the matrices D and P such that A is PDP inverse. It means you have to just do this, which I'm going to do now. Now I will write D where my first eigenvalue, because it was 2 by 2, so I just have 2 by 2 matrix. Lambda 1, 0, 0, 5. This is my D and P. P is V1, V2, only 2 eigenvectors. So P is 0, 1, first eigenvector, 2, 1, second eigenvector. That's it. You just have to write that. Now, if you want to verify, this will definitely gives you A is equal to PDP inverse. If I multiply P here, what you will get? Or you will get AP is equal to PD. You can verify this. To verify this one, you can verify this. AP is equal to PD. It's optional. If you want to verify, you can do that. You can write A. A was 5021. 5021. Multiply with P. AP. P is 0211. If you multiply, it gives you 5 into 0 plus 1 into 0. 5 into 2, 10 plus 0 into 1. 2 into 0 plus 1 into 1, 1. And then 2 into 4 plus 1, 5. Now multiply P with D. P is 0211. And with D, D is 1005. It should give you the same answer. 0 plus 0, 0 plus 10, 1 plus 0, and 1, 0 plus 5. So see, both are equal, right? So this is a verification. No need to verify. If your P and D, you are convinced that my P and D are correct, you can stop there. Verification will prove that your eigenvalues, eigenvectors are correct. So because AP and PD are equal, it means that your A is automatically PDP inverse because P goes there and becomes inverse, P inverse, right? So no need to find P inverse and multiply here. So this is just an extra step in 5.3. So I can ask you some question. I may give you a question like this. I give you a matrix A. Given a matrix A, I can split into 2 parts that, let's say in A part, find eigenvalues, right? So the first part that I did at the top, you can find lambda 1, lambda 2, so on. Then I can ask you, OK, now for those eigenvalues, find eigenvectors, right? So you can one by one, you can find eigenvectors. You can call the first eigenvector V1, call the second eigenvector V2, and so on. Then I can ask you, OK, write, not find, because no need to find, everything is done. write D and P such that P is such that A is PDP. So it means now from here, you will just do for C part, you will just do this one. You can write A as, remember, if your first eigenvalue is lambda 1, then you will write your first eigenvector V1. Do not change their location. If you write second eigenvector here, then use second eigenvector here. Don't, if you change, it's your choice. You can write lambda 2 first. But if you write lambda 2 first and lambda 1 secondly in D, then in P also write V2 first and V1 secondly. Then it's still fine, no problem. Whatever eigenvalue you are writing first, write the eigenvector for that eigenvalue first. Okay, and so on. That's pretty much it. In complex analysis, how much time is done? Time is not coming here. My time. It's almost 1 hour, more than that, right?
1.5 hours.
Okay, so we have for that we have it's not very old complex numbers and stuff like that. In complex number, some Z1, Z2 will be given A plus iota B, Z2 C plus iota D, or one complex number is given. I can ask you the conjugate of Z. Conjugate is when you change the sign of iota only. Mod of Z, right? Mod of Z is A square plus B square square root, right? Argument of Z is tangent inverse B by A. So you can just put these numbers in the formulas, find mod, stuff like that. You can add two complex numbers, subtract two complex number. You can multiply Z1 with Z2. You can divide Z1 with Z2. So these type of algebra with complex numbers, right? So this is what you should know. I think there is a video for that as well, right? So you can check out this one. This is very easy. We have different complex numbers along with their videos. So these things were easy. Multiplying, dividing, everything is easy. The important part may be this one. You know how to multiply, divide, right? It's not difficult at all. Let's say if I quickly do this, Z1 multiplied by Z2. If you have a complex number 1 plus 2 iota minus 3 plus iota, whatever that is, it's irregular. Like multiply 1 by 3, 1 by this, 2 with 3, 2 by this. But remember that iota square is minus 1. When you multiply this 2 iota with iota, it becomes 2 iota square, right? 2 iota square is minus 2. You have to remember that iota square is minus 1. So whatever you are doing, your answer should be a real number plus another real number with iota. Always remember that. You have to finish your answer like this. Real number plus iota, real number. Real plus real iota. Real plus iota, real, whatever. This should be your answer all the time. If you are dividing two complex numbers, Z1 divided by Z2. Let's say Z1 is 1 plus 2 iota. Z2 is minus 3 plus iota. You cannot leave it like that. What you do, you multiply and divide by the conjugate of the denominator. Conjugate of the denominator is 3 minus iota, right? Plus iota becomes minus iota. Multiply, divide by the conjugate. Now at the top, you have just multiplication that we did at the top. We did here, multiplication. Divided by, see, this is A plus B, A minus B. So it becomes A square minus B square. So see, this iota square becomes -1 and there is no iota in the denominator now. So the denominator becomes 9 plus iota, which is 10. So see, no iota in the denominator. At the top, when you multiply these two here, you will get a real plus real iota, right? So you can just divide 10 now. Whatever you get here, whatever you get here. So you will divide this first answer by 10 plus second answer by 10 iota. Okay, so for example, let's say if you want to do it, let's say we can multiply, no issues. This is 1 into -3, 1 into minus iota. This is minus iota. Then 2 iota into -3 is -6 iota. 2 iota into minus iota is -2 iota square. -2 iota square is +2, right? So minus +2 -3 is -1. And minus iota -6 is -7 iota divided by 10. This is what you got. Right, so you can add this -2 into -2, which is +2, basically. So -3 plus 2 is -1, and minus iota -6 iota is minus iota. Now you can write -1 by 10 and -7 by 10 iota. So see, real plus iota real. That's how you can divide two numbers. An important thing is the polar form of Z. Polar form of a complex number Z, A plus iota B. What is this? Polar form of the Z is this. Z is equal to R into cos theta plus iota sine theta. Okay, where R is the mod of Z, you can find the mod of Z as R, A square plus B square, and theta is argument of Z. Argument of Z is tangent inverse B over A. So you get this angle, write this angle in terms of pi. Okay, in terms of pi by 2, pi by 3, like that. Okay, and this will be a number. So just put this number here, put the answer. If this is just, I'm giving you the example. This is the polar form of Z. Okay, so whatever you get, let's say if you get 2 here, and let's say if you get pi by 2 here, then put this 2 for R and pi by 2 for theta. It's just an example. Of course, you will get some answer when A and B are given to you. So you can see the last part of the video that we have under the complex number. At the end of the complex number video, you will see this polar form. So polar form is important. You can do that. And in vector calculus, in vector algebra, you have simple addition, multiplication, dot product, cross product of vectors. I will ask you the question from here. Here, the important things were, if a function of x, y, z is given, a scalar function, right? Then you can find the gradient of this scalar function, which is del phi. It is partial phi by partial x I. It's a vector. Partial phi by partial y j plus partial phi by partial z k. Right? So you just have to take the 3 partial derivatives of phi and put here. If your vector f, which is f1i plus f2j plus f3k, this is your vector function, not a scalar function now. It is a function, but a vector function. Then you can find 2 more things. One is called the divergence of f, which is del dot f. Del dot f is, you take the partial derivative of f1 with x, f2 with y, and f3 with z, and just add. There is no ijk here. The answer is a scalar. There is no ijk. f1 with x, f2 with y, f3 with z, and just add them. And there is another thing which is called the curl of f, del cross f. So I will give you, let's say, a scalar function phi or a vector function f, and I can ask you to calculate these 3 quantities. It will be very straightforward. You know that the cross product is by finding this determinant, where we write the delta in the second one, partial by partial x, partial by partial y, partial by partial z. And we write the components of vector f in the third row and find this determinant. You know how to find this determinant. First, you will take I, delete these two, f3y, f2z, right? Partial f3y, partial f2z, and with I. Then minus with j, you will have the second row gone. So x of f3 and z of f1, right? So that's how you can complete the determinant, and you will get the curl of the matrix K. Now for K, you will remove this and x of f2, f2 of with x and y of f1. So this is your vector. Answer is a vector. So let me write this formula again by removing these things so that it is not confusing for you. I, j, k, partial by partial x, partial by partial y, partial by partial z, f1, f2, f3. Okay. Partial by partial x means partial derivative of x, f with respect to x. When you take the partial derivative, y and z remain constant. With respect to y, x and z remain constant. With respect to z, x and y remain constant. Now, if divergence of f comes out to be 0, we call f solenoidal. Solenoidal. That's the name of f. And if curl becomes 0, if you find the curl of f and this come out to be a 0 vector, we call f irrotational. F is irrotational. Okay. So I may ask you that find the divergence of f and curl of f. Then I can ask you, is f solenoidal? So you will just see the answer of divergence. If divergence is not 0, you will say that no, f is not solenoidal. And if curl of f is not 0, you will say that no, f is not irrotational. But if curl is 0, you will say that yes, f is irrotational, right? So again, the video for that is also posted. My video has become very lengthy. So only calculus. You may need vector algebra, but I will ask you question from here, from calculus. So again, you see the video is also there. So you can go through it. Only concentrate on finding. This video will be long, but only concentrate in finding these three quantities. Don't go into very details. Only finding these quantities is important. No need to go through very much detail. OK, and complex number as well, whatever I have reviewed here, these are more important things in complex numbers as well. OK, so the video has become very lengthy, but I hope it will help you. So try to at least cover these things that I covered here. Try to do at least 1 or 2 examples for each topic that I covered here. Then you will be fine for your exam. So let me stop there.
I have one question. Can you go back to the eigenvector thing when we solved one example?
Here, right?
The final step of finding the eigenvector. Can you repeat it?
This is the writing a vector in terms of a parametric form. You know, in section 1.5, we did that because my vector is x, right? And what is x? X is x1, x2. It's A is 2 by 2 matrix, right? Let's say if your matrix is 2 by 2, right? And you are writing ax equal to b, it means if a is 2 by 2 a, b, c, d, then your x also has just 2 unknowns. And b also has just 2 values, b1, b2. So when you are writing your x, eigenvector x, because I am solving a minus lambda I x. If a is 2 by 2, then x is also 2 entries only, x1 and x2 only, right? When you solve a homogeneous system, usually one of the variables is free and you write x1 in terms of x2. Let's say x2 is 3x2. So what I will do, and x2 is free, let's say. So let's say I will replace x1 by 3x2, but x2 does not have any value. So x2 will remain x2. Now I will take x2 as common outside and I will write inside you will get just 3 and 1, right? That is your solution. So I will just call this as my eigenvector. I will say that my eigenvector is just 3, 1, because I am only interested in the direction. You see, my direction is eigenvector. This, by changing the value of x, I am only changing the length of this vector, not the direction. If I take, instead of x2 equal to 1, if I take x2 is equal to 2, it will become 6, 2. So 6, 1 will be just double the vector, just double 2v, right? So direction does not change. So I can just pick the easiest possible thing, x2 equal to 1, and remaining vector will become my eigenvector. Is that clear?
Yes, thank you.
Anything else? All right, guys, good luck then. I'll stop the recording here.
Mr. You'll send the link for this recording, yes?
Yeah, sure,
the
sure.
Outlook?
Yes,
Yeah.
why not? I will post both PDF file as well as the link.
Okay. Thank you.
You will find the link right here as well when you come back to this